In this video, I'm going to show how to generate text word by word using a recurrent neural network with an LSTM long short-term memory layer. And so I'm going to walk through this example to show how this is done. Click on Open LiveScript to open the example. And we are going to use the Gutenberg.org as a source for the text to train the neural network. This is the novel that we're going to use for training. It's called The Count of Monte Cristo from Alexander Dumas, the same author of Three Musketeers. And so here you have all the whole text. So we're going to read this into MATLAB. Okay, so here's the URL of the same page that we just saw. And we're going to use WebRead. This is from MATLAB Web Services. And we're going to get the code. And with this we get the full HTML, and we're gonna get the HTML tree and then find the paragraphs within the text. And now we have the paragraphs, but still okay, just to make sure, I'm gonna read it again. Okay, I'm gonna read this again. Okay, now I got the subtrees, and then we're gonna extract from the subtree the text data. Takes a while. Okay, we have the data, but still is in HTML. So actually not at this point. Once you call extract HTML, we just have the text data. You can see it in here. And we're gonna get this is an example. We have the raw text. We have a total of 374 lines of paragraphs, and we're gonna get rid of the empty ones. So that is a total of only two lines. And now let's get a summary through the word cloud command to see what words are the most common in the text. Yeah, so this is basically the most common words. Okay, so as any other deep learning program, the first phase is to get the data, then prepare the data for training, get it in a way that the deep learning network can use it. Then we create the network, we provide the options, and we do the training, and eventually at the end we validate and verify that we are getting what we expect. Okay, so first step is tokenize the document. So with here, basically we break each statement into tokens, and then we're going to use this data store. This data store is going to do the padding per batch. It's going to do various things, and this is the class for it. I'm going to put some breakpoints just to see how it works. And one of the interesting details is that this is implementing the data store interface and also the mini-batchable interface. And the deep learning toolbox is when training the model, is going to interact with this data store. So it's going to give us an idea of how it works internally. Okay, so I'm going to give pause because I'm going to put breakpoints here. Okay, some of the methods here are the documents, which are basically the raw text, encoding, the mini batch size observation, and the current index in which you are iterating. Okay, so now we're gonna pass the tokenized documents and create the data store. This is the constructor. So that'll take us to the constructor. From here, we tokenize the start of text and use redmat because we're gonna append this is the number sample, so it should be 1400 or something like that, and we're going to create a column of start tokens. You can see it in here, and we're going to append that at the beginning of each statement in the document. So now you can see here that we have the start token at the beginning, and we're going to capture that raw text into a field, set the minibar size to 128. We're gonna create a word encoding. That's gonna be our dictionary, and you can see in here we have the vocabulary, a total of 18,000 words. It's a lot of it. A number of observations 14,000, and we capture the number of observations, and we start the index at 1. Okay, so let's continue. That's the constructor, and now we're gonna sort the data store, and the reason for that is because we have statements of different sizes. Even if this is poetry, the number of statements is never guaranteed to be of the same size, and the deep learning network is expecting the data to be have sequences of the same size. So because of that, we have to do padding, but padding can be detrimental to the training, especially if you have mixed lines. For example, one line of 500 words and another one of one or two, 3 words. Then the padding is going to be like 400, 300, 200, and that's going to be terrible for training. So a technique that is usually done is basically sorting the the statements from very small to very large. And the reason for this is because then you can have batches in which in a batch they're gonna have similar sizes and the padding is relative to that batch. So basically the padding is minimized. That's one thing. Another thing is that the biggest padding effect you're gonna get at the beginning where everything is chaotic, the weights have a way off a calibration, and then you leave the best data for the end. So when you are doing the fine tuning, that's when you use the best data and use the worst data at the beginning. Okay, so let's sort and see what happens. That'll take us to here. We're gonna make a new data store by copying the current one. We get the documents and we got the lengths, and you can see that they are varying sizes, and then we sorted, and using that now we get if we apply this again to the documents, the one that we created, you can see that now they are sorted. 500 is the maximum, and about 36, that's not even the minimum, that could be less than that. Okay, so we have it sorted, and let's get out of here. And now let's continue. We have the data ready. Now let's create the neural network. So the embedding dimension, that is for the semantic vector of the embedding, is going to be size 100, and that's going to be the same size of the LSTM hidden units. And the input size is 1. In this data, text data, you're going to have 3 dimensions. One of them is for the batch, that's the observations, and the other dimensions is for the words. We have only 1 word, so the second dimension is only 1 element. That's why we have this input size is 1. And the third dimension is going to be the sequence size, and that is going to depend on the size of the maximum size of the batch. Okay, so the number of words, we get it from the vocabulary, and that's going to be the output, because the output is going to give us a word. What is the word with the highest probability? So basically you have to give a vector of all the possible words, and that's why the number of classes plus 1, that will be the terminating character or the start character, is going to be fed to a fully connected layer that is going to give you a classification. We're going to use a dropout for regularization and LSTM for actually doing the core of the network to train for sequences. And the embedding is the one that is going to convert us the word coding from a number to a vector of values, which is going to give us the semantic information of the word, and that word is fed to the LSTM. Okay, so let's just quickly visualize it with analyzed network and layers. Okay, we can see that we have no errors, and we have the input 1 word, the embedding, the hidden units, and then we do a word classification at the end with a dropout. Okay, fine. The training options here are pretty default. We have that at the moment algorithm. We have 3 max epochs, 300 epochs. That's a lot. In convolutional problems, we see that epochs of 5 take a lot. But here we have a small network, so we can take the luxury of training a lot. So the initial learning rate is 0.01, and we are never gonna shuffle because we have the sorting going on in here, and we don't want to mess up with that. So let's just take the options, and once you have the layers, you have the options, and you have the data store, you feed all 3 data store, layers, and options to train network, and we get a train network. Okay, so now let's give it a shot and train it. Okay, so now we're hitting the breakpoints of the data store. At the beginning, we set the current index to 1. When you see that the deep learning train network is calling the train network command is calling the reset in the data store. That's the first thing it's doing. And then it calls the read to get the data, and it's going to get it in the form of a table. As you can see at the end, we're going to get the predictor and the responses. This is the expected value. Okay, so for that we need the mini batch, the encoding, and we get the start position and position, which is basically the batch, and from that we get the data. Those are a set of 128 statements. Okay, so now we're gonna using the number of words, we use doc to sequence to convert those words into indices. So we can see here, and notice that this is the terminating character. You have the padding at the beginning, and the last one, which is the biggest one because they are sorted, doesn't have any padding. And notice it's only one word that is padded. That's the advantage because we're padding relative to the maximum size of the batch, which is 5. So that's great. Okay, so now we're gonna create the predictions, and the prediction is gonna be used by shifting the input by 1 and putting the end of text at the end. We're gonna see this in a moment how it behaves. Okay, so we take the predictor, we take the indices, we shift them, we take the from the second to the last, and we encode it into words, and then at the end of text. So we convert it into words, and now we use categorical with the number with the class with the number of words here. So basically we convert them into categories, and we can see here that they are categorical type, and that's the type that we need. That's the output of the neural network. That's what you're going to subtract against the output of the network to get the loss, and from the loss you get the gradients, and you compute the gradients relative to the weights, and then update the weights of the network. Okay, so let's finish this until here, F5. It takes a while, but I'm going to show how this looks. For the first input, this is we're going to convert using the encoding the predictors, which are codes into words. So this is the first statement, and let's take a look at the responses. So yeah, this is not the one that I was looking for. Okay, let's pick up the first one. Okay, so here you can see that the first missing, because it's padding, is going to predict the start of text. The start of text is going to predict day, and day is going to predict obeyed, and obeyed is going to predict dot, and dot is going to predict the end of the text. So notice that there's a shift. This goes here, actually this is here, this is here. So the sequence is shifted to the left one, and then the end of text token word is added to the end. So basically the same text is using to predict the next word, and that's what you provide here for the network to train. So it's going to form a table with the responses. No, it's in the data actually. Yeah, you can see a table here. And basically the neural network is going to feed this to the input, get the output, and subtract it against the responses to get the loss and the gradients and train the network. Okay, so let's take this breakpoint away because it's going to be called many times for each batch. And now one of the breakpoints that is going to hit is this one to know if it is finished. So it's the batch size from the process current index, which should be some low value for now. And once the number of observations of 14,000 is exceeded, then it finishes. So let's take this away. And now the training is going to start. We're going to see the progress. Okay, so here's the progress. This confirms that we're using the GPU. Yeah, so we're gonna get some update on the accuracy and also on the loss. So this is very slow. It's a 30% accuracy, and is pretty good for being the first epoch. The problem is that it might take 10 or 20 minutes to go to a second epoch, and this is because the text is very big, But if you leave it enough time to get to the epoch 300, probably you're gonna reach an 80 or more accuracy under this. But the text is too heavy. I mean, the Count of Monte Cristo seems to be a very large novel, and but this example actually was suggesting Alice in Wonderland from the same Gutenberg project, and that's a very short novel. So I'm gonna actually I run that in this example, and was able to get, you see the nature of the oscillation of this pretty rare, but eventually gets to 80%, and the loss goes down to very low, and it took 32 minutes to complete. So I basically saved that network, and I'm going to use that network for the rest of the example. Okay, so I saved the network in TrainNet. So now we have the saved network in here, and that's the one that we're going to use. And we're going to get from the data store the encoding, but probably that's not going to work. I have to use the encoding from Alice in Wonderland, so I'm going to hit pause and get that. Okay, now we have the encoding, but this is from Alice in Wonderland. We encode the word index, which is index number 1, and we get the vocabulary from the last layer, which is the classification layer. We get all the words, and this is yeah, it uses 3,000 words compared to the 18,000 words from the Count of Monte Cristo, and yeah, that's why it took so much to train. Okay, so we're gonna run this to generate the text. For that, we're gonna hit a breakpoint here. Okay, so the first text is gonna be as we said it's gonna be the start index. So if we convert this word to in, no, actually it's the opposite. I'm gonna get that command. Okay, so here's the command, index to word. You have to pass the encoding, and we have start text. That's gonna be our first character. Okay, so we're gonna set it to run the CPU. It's more efficient for this case, and we're gonna use the predict and update state because this is gonna predict the next word, but also update the state of the LSTM layer, which is a recurrent neural network, a recurrent layer which has a state. Okay, so the state is updated in the network, so we get the network as the output, and we're gonna get the scores. The scores are the probability of the next word. So you can see almost at the bottom that we have like 89% for one of the words, and that should be the next word. So we use data sample, which is a function from the statistic toolbox that is going to take the vocabulary and the corresponding probabilities, which are set as the weights. So if we always select the word with the highest probability, it's going to be kind of boring because it's going to give us a deterministic result always. But this is going to randomly take the next word based on the weights, on the probabilities. So yeah, so we got that the first word is a quote, and it's not the end of text, so we don't finish, and we're gonna have a blank generated text. We append it there, and we're gonna convert the new word into an index, and that's gonna be the next index, and that's gonna give us our new words. So, and we keep going, new word. So we keep going. So you don't, kind of makes sense. So you don't like that. That's very nice. So you don't like and I found a more convenient to do prediction word by word rather than a character by character. Things kind of make a little bit more sense, and I think that is because one is that a if you capture things word by word, you don't commit the mistake of generating words that do not exist. Second, when you do embedding, the embedding is capturing the semantic of the word, and you do a training based on the semantic of the words and the connection between them through the LSTM, the memory that it has. So kind of the statements make a little bit more sense. Okay, so let's run it to the end. And now at the end, we remove the spaces around the punctuations using the replace method. You can see the whole command in here. And finally, we reset the network, the state, so that we can generate more text. Okay, so the first statement is, so you don't like this, so you don't like cats. That's pretty nice. Okay, so now let's try it again. Let's run it. For the griffon suddenly went on looking for the poor saint and said, I wish I hadn't cried about her. This is pretty nice. Okay, so let's run it again. Hit an angry tone. He looked at the minute when it was long time with the sun. Okay, so here you have it. Thank you very much for watching.